Today we are going to solve problems with binary search. For binary search to work, we need to get a middle element and we have to decide whether to go left or to go right. That is to divide our search space. Only after dividing our search space can we reduce our time complexity from order n to log n. Our first problem for today is what is the frequency of k? We are given an array of elements and we need to find an frequency of any element given here. For this problem, let us suppose that k is equal to 5. Now the naive approach can be to go through a linear search and find the frequency, but the time complexity of that approach will be order n. We can have, have a better approach which is more efficient, known as binary search. We can find the first occurrence and last occurrence of k, and the number of elements between those occurrences will be the frequency of k. Now to get the first occurrence of k, we will first initialize our left to 0 and our high value to length minus 1, which is n minus 1, number of elements minus 1, and our mid will be l plus h divided by 2, which will come out to 3, 5, 6, 7, 8, 9, 10. So we have 10 elements. The first mid hour will be 5. Should be 1, 2, 3, 4, 5. Now we check A of m double equals to k. In our case, array of 5 is equals to array k, but we know that this is not the first occurrence. To find the first occurrence, there is a possibility that this can be first occurrence or the first occurrence can be on the left side. So if this is true, we'll initialize our first occurrence value. Let's say first equals to m, and we will reduce our search space such as h equals to n minus 1. We'll simply take a first occurrence and initialize it to 0. Else, if a of m is greater than k, then we need to reduce our search space to left side such that h equals to n minus 1. Else, if a of m is less than k, then we'll increase our search space to the right, n plus 1. Now we can observe that we can uh, merge these two cases such that we have these two approaches. Now we know that if it's equal to or less than, I'm sorry, or greater than or equal to k, we need to move our search space to the left by decreasing the h value. Now after this will continue while L is less than equal to H. These two if and else conditions will continue as long as L is less than equal to H. Now after this while loop is completed, we will have a first occurrence. Similarly, we can get a last occurrence. For last occurrence, we just need to for last occurrence we need to be moving this to the right side. Which means whenever we encounter equals to k, we need to it can be a possible the last occurrence and we need to move our left to m plus 1, and this will be less than equal to k. Whenever it's less than or equal, we need to move our search is right, and else if a of m is greater than k, last will be m, h will be n minus 1. With the previous we will get our first occurrence, and with the next this return we will get our last occurrence. After getting our first and last occurrence, we just need to count the number of values between them, which will be returned last minus first plus 1. So let's say our first is here and last is here. So, the indices of first will be 4 and last will be 4. We will be returning 7 minus 4 plus 1, which will be equal to 4. So as you can see, the number frequency of pi is for 1, 2, 3, 4. Now we'll go to our second problem, which is to find the peak element. The peak element will be an element which is greater than its previous element and its next element. For example, 6 here is a peak element, as you can see it's greater than 2 is not a peak element, 5 is not a peak element, 7 is not a peak element. As for the boundary elements, they to check if they are peak elements, we just need to check if one is greater than the next element, whereas one is not the peak minus one is not the peak element. But for the n element 8, which is greater than its previous element, we don't have anything to check on the right. So yes, this is also a peak element. Now our problem is to solve and return any peak element. The naive approach will be find the max element in the given array and return that element. As any array of distinct elements will have one unique max element, we need to return that element. The time complexity of that approach will be order n, but we'll improve that to binary search. First, we'll just check whether if first and last elements will are peak elements or not. If a of 0 is greater than a of 1. If this is written this, then return a of 0. Since a of 0 is our peak element, we need to have another check if a of n minus 1 is greater than a of. If this fails, we'll check this condition n minus 2. That is we are comparing last two elements n minus 1 and n minus 2. If n minus 1 is greater than n minus 2, then means that this is a peak element. Return a of n minus 1. These two are our edge cases. Now we need to initialize our last one, since we have already checked for the zeroth element at the zeroth index and at the n minus 1 index. So we don't care about them. And our h will be n minus 2. Now there are two possible conditions. The possible conditions whenever we calculate m, we are l plus h by 2. Now a of m can be greater than a of m minus 1, and also a of m can be greater than a of m plus 1. If it fulfills these two conditions, then we will return this as the peak element. So if a of m greater than a of m minus 1 and a of m greater than a of m plus 1, return a of m. Now we have checked one condition. Now the other condition will be a of m minus 1 will be less than a of m, which will also be less than a of m plus 1. So in this condition, we know that a of m cannot be a peak since it's not greater than its next element. But there is a possibility that a of m plus 1 is a peak element. It, it may not be a peak element, but there is a possibility since it's greater than its previous element. So we will increment our L value to n plus 1. We will shift our search page to the right. So let's start if a of m is less than a of m plus 1, then our L will be m plus 1. And the other condition will be the reverse of this. Our a of m element will be less than a of m plus 1, but it will be greater than m plus 1. Even in this condition, a, a of m will not be a peak element since it's not greater than its previous element. But the previous element can be a peak element. There's a possibility. So if else if a of m is less than a of m minus 1, then h equals to m minus 1. Now in the next iteration, this will go on till while L is less than equal to H. At some point, we will find a peak element and return this. Since in the array, as I stated in the array of existing elements, there will be one peak element in the max element. Now the time complexity of this will be log n. Now I'm going to share the codes of these two. This is the code of frequency of k. So we'll first find the first occurrence and the last occurrence. For the first occurrence, if answer is will stay, this can be a possible first occurrence. And if we are finding the first occurrence, which means we'll decrement our search to the left side, which will be h equals to m minus 1. Else, if you're finding for the last occurrence, we'll increment our L to n plus 1. Else, if a of f is less than k, which is for a sorted element, we'll increment our search with, otherwise we'll increment our search with. We'll calculate a of we'll also calculate the median. And this will go on until we find our first occurrence. We are calling the first occurrence with the true value, hence it will be calling always decrementing our search with to the left side. And we'll get our first occurrence here, f int of f4. And similarly calling for the last occurrence with false. And it will be decrementing our search with to the right and using plus 1. After both of these functions have been called, we will have the first occurrence for k and last occurrence of k. We'll simply return L minus L2 plus 1. Now I'll share the code for peak element. Now for peak element, we will have some basis array of size equals to 1, then in the first element will be the peak element. So we return an index of 0. Else if we are checking only if the first element is the peak element. So first if we return the element at index 1, we return element at index 0. Similarly, check for the last index if element at last index greater than element of last index but 1, then we return the element of last index. Then we'll initialize. If none of these conditions are true, we'll initialize our left 1 and low 1 and height size minus 2. and our answer will be initially at the element at index 1. Now we calculate our mid, and we'll check whether mid is a peak element or not. We'll check by if mid is greater than equal to n plus 1 and greater than n minus 1, then our answer will be initialized to array of mid. Else if mid is less than n plus 1, then we'll increment our we'll go to n plus 1. Else if decrement height to n minus 1. After this while loop has been completed, return our answer. Our answer will contain the peak element. Now we'll go on to the final question, which is the unique element. As the question says that there will be only one unique element, that is which will occur once. Rest all the elements will occur twice. The another constraint will be all the elements which are occurring twice will be together. As you can see, 3 and 3 are together, 1 and 1 are together, 8 and 8 are together, so on. Our unique element is 19, which is occurring only once. But mind that the array is not sorted. Since you can see 1 is coming after 3. The only thing that is mentioned is the elements that are coming together will be elements that are occurring twice will be together. Now, the one thing to be observed is in the elements before this is our unique element. In the elements before the unique element, the first index of the of the elements that are occurring twice will be even. So you can see the first occurrence of 3 is at 0, at 1 is at 2, of 8 is at 4. Now, since this unique element is coming only once, it will disrupt this property, and after this unique element, all the elements first occurrence will be at odd occurrence, 9, 11, 13, and so on. Now, as I stated before, the, in binary search, we need to determine if we are going to left or right. In this problem, we can determine it by calculating the first occurrence. If the first occurrence index is meaning is even, that means you have to go right. If the first occurrence index is odd, that means you have to go left. Now first we have the same base conditions as before. If size equals to 1, then means that for a let, let n be the size. If n equals to 1, then return a of 0. If now we check if this is a unique element or not. If at index element at index 0 should be unique, it should be equal to index 1. A of 0 not equals to A of 1. That means return A of 0. If A of n minus 1 not equal to A of n minus 2, return A of n minus 1. Now, as after completing our base solution, we will again initialize the value of 1 high to n minus 2, and we'll calculate mid equals n plus h by 2. Now, first we'll check as usual. We open our while loop till L less than equals to h. Now, first we'll check if the element at m is unique or not. A of n is not equal to A of m plus 1, and A of n is not equal to A of m minus 1. Then return A of m. Now, else else we need to get the first occurrence. If a of m equals to a of m minus 1, that means that m minus 1 is the first occurrence. So m equals to m minus 1. If a of m is not equal to a of m minus 1, which means that only m is the first occurrence. So we won't update m equals to m plus 1. Now we will check if m, we are checking if the index is even or not. Now we know that this is even. So we need to update our low value. We need to shift our search to the right. So we will update to n plus 2. Since you can see that if our first occurrence in that array, we jump at we jump at 5. We check whether it's equal to its previous element. So I it here n is equal to n minus 1. If it's equal to previous element, we'll first n will be updated to 4 as it will be the first occurrence of 8. Now, since 4 is even, we need to jump to the right. We cannot jump to m equals to n plus 1, which will be 5. Since in this search space, there will be two unique elements, 8 and 19. So we need to jump m such that m equals to 4 plus 2 will be 6. Let me erase this. We need to jump our search space here. As you can see, we have only one unique element. So if it's even, we jump m plus 2. Else, else we have to reduce our h value m minus 1. We are reducing h minus 1 only to 1 because uh, in the right side m will be at on. So m will not be equal to its previous position. It's at the odd positions, it will not be equal to position. So m will be at on. To reduce the surface, we only have to jump 1. If we have m is pointing to 11, we have to reduce n to 10. So that here we have to reduce the switch. Now we'll complete our else. As you can see, else is completed, and after that function is also completed, while loop is also completed. It will return which is the unit element. I hope you have understood the three questions we have discussed. Now I'll show you the code of the unique element. Now you can see we are checking the base conditions if size is 1, or if you're checking the index 1 is unique, or the index element at last is unique. Again, we initialize our one height n minus 2, and we initialize our answer to the element at index 1. As you can see, we'll check, we are calculating length, and now we are checking if element at index n is unique. So we'll check if not equal to m minus 1 and not equal to m plus 1. We'll initialize the answer yet of n. Else, we are checking if this is the first occurrence. If of m is equal to m minus 1, then this is not the first occurrence. We'll update m minus 1. Now we'll check if m index is even or not. If it's even, then we update our L to m plus 2. Else we reduce h to m minus 1. After completion of value, we will have our answer, and we will return our answer. I hope you have enjoyed this. Thank you.